In the previous video I demonstrated the effect that old failing ICs can have on circuit performance. I had 5 ICs and 2 of them were ICs that were failing and underperforming. 2 of the ICs were new old stock, they're actually the ones I used to repair the board I got the failing ones from, and then we had another one from the same board, the original from the same board, but one that tested good. And I was trying to demonstrate the difference in performance between the different ICs. Now they're all the same manufacture type, they're all the same date code, so they should all really perform in a pretty much identical manner, at least within a few nanoseconds of each other. But as you saw in the video, if you watched it, the failing ICs were underperforming and they were causing issues. Now I demonstrated the effect using this circuit and it seems to have caused a bit of confusion. I think most people understood what I was trying to demonstrate, but the point here is it's not meant to be representative of a circuit you're going to find in a vintage computer. It was really set up to work as a logic comparator to demonstrate the difference between 2 separate signal paths. And I've received a couple of comments that raised some interesting points, so I thought I would address those before we really get started on the next step in this series. And the first comment was that well, if it's a case of having a circuit like this that creates a race condition, then it's poor design. Well, that's not what I was trying to demonstrate. I was trying to demonstrate the difference in the timing, so I think that's just a bit of a misunderstanding of what I was trying to demonstrate. I was really trying to show that as ICs get old, they can fail to perform the way that they should, and that can cause problems within a design. So got a slightly different circuit here we'll have a look at in a minute, but we'll just address another couple of points that came up that I thought were quite interesting, so I thought I'd respond to them here. So the first one was the use of a breadboard to demonstrate this sort of thing, and the comment said that it's not a valid way of doing this because the breadboards, or the breadboard itself, will introduce delays. Well, no, it won't. It's not really the issue with breadboards. The problem with breadboards is the capacitance and the contact resistance, and yes, it can cause issues, but not in a circuit like this. And what I was trying to do was set up an analogue of a vintage computer board, and vintage computer boards usually quite big. The layout is usually a result of expedience in manufacturing and whatever else, but they're not necessarily impedance matched traces and that sort of thing. So a setup like this is very analogous to a vintage board, which is what I'm really trying to demonstrate. But either way, it's not going to have a bearing on the signal timing, and I demonstrated the circuit using multiple probes, 4 different scopes, different configurations, different ICs. I even put a capacitor onto one of the signals to demonstrate the difference that would have. So don't worry about the fact this is being shown on a breadboard. It will have absolutely no impact on the outcome of the testing. The second comment was from the same person, and kind of the same sort of thing, is saying that well, the length of the ground leads on here is going to have a major impact, so it's just lucky we got the results that we did. No, I'm sorry, that's just incorrect. If you've been watching my channel for any length of time, then you'll probably quite often see me using test leads without a ground lead attached at all, and I will demonstrate the effect that has in a few minutes. But it does not affect the timing. It will affect it to a small degree, but not for what we're looking for and not for what I am trying to explain here. The effect of not having a ground lead will be to give you a very poor signal, but if you know what you're looking for, which is what I'm trying to get across here, then having the ground leads attached or having the ground leads longer than they need to be is certainly not going to have any bearing, and I will demonstrate just how little effect they have a little later on in this video. So don't worry that this is a breadboard, it won't impact the results. Don't worry that we've got these ground leads that are a few inches long, it will have absolutely no bearing on the results. And if you're testing a vintage computer board, then this is probably the best type of setup you're likely to use anyway. So as I said, I'm trying to set up here an analogy for testing vintage computers. So thanks for the comments, but in the context of what we're trying to explain here, then they're not really valid, and this type of testing is still perfectly correct. Now, one other thing here is that this is by way of a demonstration as to how to go about using a scope to try and find faults on a board. I'm not suggesting that you do this sort of testing with all the ICs you remove. So you don't need a signal generator, for example. You just need the scope, and I'm trying to demonstrate here what you're actually looking for. So to try and drive the point home about the use of grounds connections, I will disconnect these now. So on the scope we've got 3 signals showing, and I will show the circuit that we've got on the breadboard in a minute, but just for now what we have are 3 signals. The yellow trace is the clock going into the circuit. Now, it's not the clock directly from the signal generator, it's going through a TTL 74 LSO4 just to clean it up and make the signals consistent throughout the circuit. And the purple and blue traces are the output of the 2 ICs, one new, one old. And what I'll do now is disconnect the ground leads so you can see what effect that will have. So we'll disconnect the first one. Now, of course, these are all connected to the same scope. So long as you have one connected somewhere, then it's going to be a valid ground path. So let's get the last one off. So as you can see, it has almost no bearing on the signal at all. Now, these 2 probes here are actually going to a different scope. I'll demonstrate what these are for later on, but I've got them connected now just so that we don't change the test conditions when we look at a different scope. But as you can see, the signals are still perfectly fine. There's nothing wrong, and you can use probes like this with the ground lead disconnected. In fact, I normally remove the ground leads, the ground leads on the probes completely, just to make it a bit easier to test. I do sometimes attach them and find a local ground on the board if I'm looking for a very specific signal or want to examine a signal in more detail, but as you can see, you don't need these connected, and it will have no real bearing on the testing that we are carrying out here. Having said that, I will reconnect them just to make sure that I don't upset anyone, and also to keep the test as consistent as possible. Okay, so we've got those reconnected. Has cleaned up the signals a bit, as you'd expect, but it's not had any major impact on what we're looking at. So now we'll go into the next step in this video series, which is to look at why failing ICs can have such a major impact on a vintage computer operation. So firstly, we'll look at this circuit that we have here, and I'll explain why I've configured it this way in a few minutes. So what we've got is a series of 4 gates, and they're in 2 strings. Now, I'm not trying to suggest here that you would set this circuit up, because again it might upset people thinking there's a race condition going on here. What this is meant to represent are 2 separate chains of gates, one terminated at A, one terminated at B, and it's just so we can examine 2 different IC performances at the same time. I'm not suggesting that you set up a circuit like this because you would end up with a race condition, but what we can do with this circuit is look at the output at A and B and see what impact a failing IC has on the relative timing of the 2 signals, and then I'll explain why this is so important. So the issue that we tend to get in vintage computers, vintage circuits in general, is best explained by looking at the data sheet for the processor. So in this case we'll look at the data sheet, or part of the data sheet, for a Z80, and in particular these are the memory read and write cycles, or parts of the cycle. And what we have, of course, is a clock that drives everything on the board. So almost every signal is derived from the master clock, and at some point that clock, usually divided down, goes into the processor itself. But the important thing here is that all the activities on the board are governed by these clock edges. So it might be a falling edge, it might be a rising edge, depends what you're driving, but from any given edge you will have a finite amount of time to perform an operation. So for example, let's say we want to do a memory read. Then from the point where the clock falls in the T1 cycle of the read cycle, you have a finite amount of time to respond to the memory request and the read lines going low to set up your data. And that's the data usually coming from something like a RAM chip or something like that. But this time is dependent on the RAM chip. But from this point going forward, the signals normally go through, for example, the memory decoder to decode the memory space, the bank, and select the particular RAM that you're trying to read. So the amount of time that you have here might be fairly short. It depends on exactly what you're doing within the system. So for example, if it's DRAM, you have to carry out quite a few operations to get the DRAM to respond. So from the input, the clock edge going into a circuit, you could have anything from one gate, if you just got a ROM chip connected, for example, up to 6, 8 gates or even more between the signal edge and what you're trying to drive. And that's what these circuits really represent. I've limited it to 4. So this tends to be a minimum number of gates you will get in the memory decoder and memory select circuit. So the idea here is that you look at the input signal edges as the clock edges for your processor, and then going through your decoder, the resultant edge here shows you the delay between the two, and that's what we're representing here. We're not saying that these two signals are driving the RAM or whatever it is directly, but it can show a difference for, if for example one path is for the chip enable for an SRAM and the second one is for a write enable for the SRAM, and that can have a major impact if they're not correctly timed. If we look at the data sheet for a typical SRAM, this is the SRAM type they're actually using in the Z80 project for the Z80 computer I'm designing. And if we look at the timing for a write cycle, the device supports 2 different types of control for the write cycle, but both have similar constraints. From the time when you set the address that you want to write to, you have a finite amount of time before you need to perform other functions. And how you go about timing all this depends on how you want to drive your memory and what other devices you intend to drive. But the point here is that the timing is not based on a race condition, it's based on the requirements of the system, based on the clock cycles that are being provided to the processor. Now you can of course introduce wait states and whatever else, but there's a limit as to how far you can go down that path. Also, if you're introducing artificial delays using external circuits, those external circuits are also made from TTL devices that can start to introduce similar types of issues. So these timings are usually quite short, they're talking nanoseconds, and normally these individual steps within a cycle are controlled from the clock cycles of the clock going to the processor. It's all tied together to make sure everything's choreographed correctly. But the point here is, if this edge is being controlled through a string of TTL logic gates, then this time is meant to occur within a certain time window, and if the device starts failing, this can occur at the wrong time. Or worse still, the write and chip enable lines, data valid point and the addressing can all be out of sequence, in which case you can end up writing to the wrong address or more than one address, as I demonstrated in the previous video. And that's what causes it. It's when these edges occur at the wrong time. It's not because there's a race condition, it's simply because the devices are taking too long to do their job. And while the designers did a good job initially, they do expect the devices to operate within a certain window, a certain specification. And when they no longer do that, you can encounter problems. And of course, if you start getting devices that are in a sequence, then if a particular device or devices start to fail, then the overall timing effect is multiplied, and you can end up with issues. You might find that you've got a RAM that's failing a test, for example. You change a device and it starts working. Doesn't necessarily mean that's the only device you've got problems with. Another one might be failing, but the overall operation might then be fast enough for it to work. And that's what can cause confusion when you're trying to repair these. You might find that a little while later you get the same problem coming back. You might think the same device has failed, but in reality it's more likely just one of the others has got slightly worse, or something else has changed that's upsetting it. Now, before we go any further, I want to do something that I should really have done in the previous video, but I didn't, and it was a bit of an oversight, but I'll correct that now. And that is to demonstrate two different probes on the same scope at the same time. I did demonstrate different probes, but I didn't show them side by side. And we'll rectify that now. I'll move the camera, we'll look at the LaCroix, and that's a 5 giga sample per second scope, 500 megahertz bandwidth, and we'll look at one of the expensive probes and one of the lower cost probes. They're both connected to the clock output from the buffer chip, so they should both be showing the same thing. And again, yes, we're using a breadboard, but this will have absolutely no bearing on what we're looking at in terms of comparing the two probes. It might have an impact on the overall signal quality, but it's not going to change what we're seeing when comparing these probes side by side. And after all, this is how you're going to be using the probes anyway, so it's not an invalid test. So I'll move the camera, we'll look at the LaCroix and see what's going on. Okay, I'll dim the lights so you can see the screen a bit better. And what we're looking at here are the two signals from the two probes. And the yellow trace is the more expensive probe, and the blue trace is the lower cost probe. Now it looks quite bad, but the scope is showing 5 nanoseconds per division, so we're only getting a few nanoseconds error on the two probes. And this does, I have tested all the probes and they all give almost identical results, so this is not anomalous readings that we're seeing here. This is fairly typical for the probe types. So you can see that the more expensive probe definitely outperforms the lower cost ones, but at the speeds we're talking about, if we slow the scope down to something that's more in keeping with the type of signals that we are going to encounter, then you can see that you can't really detect the difference at all. So a few nanoseconds doesn't really matter. It does matter if you're working on very high frequency circuits. About 90% of my commercial designs have included RF systems, and when you're talking about hundreds of megahertz, then yes, a few nanoseconds makes a big difference. That's why I have this scope in the first place. But looking at a digital circuit on a vintage piece of equipment, that couple of nanoseconds is not really going to make any difference. So it is valid to use the lower cost probes. You don't need the expensive ones, and the same is true of the lower cost scope, although you do need a scope with at least a decent bandwidth to show squared up edges on the signals. So I'll move the camera back down. So looking back at the scope, you can see that at the moment there doesn't appear to be any timing issues. We're looking at the circuit I showed earlier. So the yellow trace is the input signal, the purple trace is the A signal, and the blue trace is the B signal. And I'll leave it to you to try and determine which of the two ICs is which. But the whole point here is that one is driven through device that's failing to meet the required specification, and the other one is a new old stock device that does meet specification. And the reason this is important, as I said, is we have a finite amount of time. So if we look at the clock cycles on the Z80 spec sheet, then if we're running the processor at 5 MHz, then of course each of the clock periods is 200 nanoseconds, but the half cycle time is of course only 100 nanoseconds. So a lot of the time we only have 100 nanoseconds to carry out an entire part of the process. If it's decoding something or switching a multiplexer or something of that nature, then the events have to be completed within a certain length of time. So what we'll do is we'll set up the signal generator and the scope in such a way that we are simulating what it is we're looking at. At the moment it's set for 1 MHz with a 100 microsecond pulse width, so it's a pulse we're looking at here. And that's another important point is don't look at it in terms of the cyclic frequency of the signal. What you're interested in here is the pulse length and width that is applied to a certain part of the circuit. But we will assume that we are running at 5 MHz. So we'll set up the signal generator to give us the frequency that we are trying to simulate. So in this case we want to set it for 5 MHz, and the pulse width we'll use, we'll set it to a 100 nanoseconds, because that's kind of the pulse width that we would normally be expecting to see on the individual clock cycles within a system. So I'll just finish setting this up. Okay, so we've got the signal generator set up to give us a signal that represents our clock cycle for the Z80. Let's turn this light back on. So we'll zoom in and have a look at that. So remember that the yellow trace is our clock and the other two traces are the outputs of our two strings of gates. So if we look back at the circuit, then hopefully you can clearly see that the blue trace represents our failing IC and the purple trace represents a good IC. And you can clearly see here that we're set for 20 nanoseconds of division. Let's get the cursors onto the screen here so we can see exactly what we're doing. Okay, so looking at the delay time, it's about 8 nanoseconds. That's extremely good. These are new old stock, but this particular circuit, if we assume that we have to complete whatever activity is going on the board within a single clock cycle, that's the Z80 clock, you can see that the rising edge of the blue trace is very close to the end of the clock cycle. And in fact, if we move the cursor across, then that's 90 nanoseconds. So it's more than 10 times the delay, and these are the same type of chip, remember, so very significant. And because we're getting so close to our 100 nanosecond limit, this is why this particular IC would cause an issue in a circuit, because the next event is about to start within the board. And this is just at 5 megahertz. If we change and go up to 6 megahertz, you'll see that we get an even bigger problem. Okay, so you can see now that we have an issue here, that the falling edge of our failing device is now outside of that particular phase of the main clock. So whatever process it was supposed to have completed, it's failed to do that, and we're now into whatever the next phase of the process would be on the board. So this will almost certainly cause a problem, but you can see the purple trace has responded quickly. The falling edge is well within the clock cycle, even at this speed. And what we'll do is just for a bit of fun is we'll increase the clock still further and see how high we can go and still have the falling edge of the purple trace within the clock period. So we'll get up to 10 megahertz. So up at 10 megahertz now, you can see that the edge of the purple trace is still well within the clock cycle, and the blue is obviously, we're now actually one phase out completely with the blue cycle. It's nowhere near fast enough to meet the requirement. We'll go up to 20 megahertz. So again, the falling edge of the purple trace is still well within the clock pulse, or the clock phase of the main clock. So even at 20 megahertz, the purple trace is still showing us a good response. And this is what we'd expect from ICs that are working correctly. I'll slow this back down so we can see it a bit more clearly. So back down at 5 megahertz. So hopefully this demonstrates the effect that we're having and clarifies the point I'm trying to get across here, which is that the output from a given string of gates in the system, in a vintage system, must occur within a particular time window. If it fails to do that, then other events that are occurring on the board are going to effectively clash with it, and the overall system is going to stop working. So what you're looking for when you're probing around the board is something like this. What you can do is just put you've got two probes, put one on the input of a device, one on the expected output, and see what the delay is. And if you're getting something that's obviously way too long, then it's going to potentially indicate that the device is failing. Could of course mean that the device it's feeding into is drawing too much current, but either way you can look at which of those two it is and start to investigate the devices. But what you're looking for is the relative timing, and of course, because the overall effect is to maybe cause issues when trying to read something like an SRAM, a good place to start is the data sheet for the devices. So if you want to investigate whether you've got an issue with the SRAM, get the data sheet for the SRAM, look at the signals going to it and see if they make sense. Make sure they meet one of the requirements for the way that the device should be driven. And if the timing is way out, then you may well have found your culprit. Do that for all the major devices on the board, and you should fairly easily track down what's causing the issue, and all you've got to do then is work your way back through the string of gates that are feeding the signal, and at some point you should find the culprit, replace it, and hopefully that's going to be one step closer to getting your machine working. Okay, that's it for this video. Hopefully this will have been of some interest to some of you, and may help anyone who's getting started in this fault finding process.